Hey, welcome to The Explainer. Today, we're going to tackle a huge topic, machine learning. It often feels like some kind of magic, right? Well, we're going to pull back the curtain and show you the actual method behind it all, the stuff that is literally changing our world as we speak. All right, let's just jump right in with a little test. Have a look at this. Can you tell the difference between a chihuahua and a blueberry muffin? I mean, for us humans, it's pretty easy, right? Well, usually. Sometimes you gotta squint a little. But think about it. What about a computer? How would you even begin to program that? You can't just write a rule that says if it has two dark spots and a lighter spot, it's a chihuahua. It's way too complicated. And this kind of silly puzzle, it's actually the perfect way to understand the exact problem machine learning was created to solve. So yeah, a computer that learns. What does that even mean? It's not just about storing information. It's something way, way deeper than that. This idea has actually been around for a while. Way back in 1959, this guy, Arthur Samuel, basically nailed it. He created a checkers program that eventually learned how to play better than him, and he defined machine learning as this: the field of study that gives computers the ability to learn without being explicitly programmed. That's the key right there, without being explicitly programmed. Okay, and this is where you really see the huge shift in thinking. With old school programming, right? You'd write the rules, you'd feed in the data, and you'd get an output. Simple. But machine learning completely flips that on its head. Here, you give the computer the data and the outputs, the answers, and it figures out the rules all by itself. It literally writes its own program. A perfect, everyday example of this is your spam filter. Think about it. The task? To catch junk mail. The experience? That's all the emails you've ever flagged as spam. And its performance? Well, that's just the percentage of junk it actually catches. Every time you mark an email as spam, you're teaching it. It's learning from you and getting better. And sometimes the patterns it finds are just unbelievable. Things we would never connect on our own. Get this. Researchers discovered that a sudden jump in bad reviews for scented candles on Amazon, specifically people saying it has no scent, was a super strong predictor of a COVID-19 spike. Who would have thought to even look for that? Okay, so the big question is, how does this learning actually work? What are the main ways we can teach a computer to think? Turns out there are a few main styles. The first one, and by far the most common, is called supervised learning. The supervised part is key. It means we give the model a ton of data that's already been labeled with the right answers. It's exactly like giving a student a study guide that has all the questions and the answers already filled in. And you see this everywhere. If the goal is to predict a number, like what's a house going to sell for, that's a task called regression. If the goal is to pick a category, is this email spam or not spam, that's called classification. But in both cases, it's all about learning from examples that already have the right answers. But okay, what if you don't have that nice answer key? What if you just have a massive, messy mountain of data? That's where unsupervised learning comes into play. You basically just dump the data on the algorithm and say, find something interesting in here. It has to discover the patterns and structures all on its own. Yep, think about it like this. If I gave a computer all these Simpsons characters and just said, organize them, what would it do? It might put them into family groups, or maybe group them by gender, or maybe it would group them by who works at the power plant versus the school. This idea is called clustering, and it's amazing for finding these natural groups in data that maybe we humans wouldn't have even seen. All right, let's peek under the hood for a second. We've talked about the what, but what about the how? We're going to do a super quick tour of a few of the core recipes, the actual algorithms that are the real engines behind all this learning. First up, for predicting numbers, you've got linear regression. This one's a classic for a reason. It sounds fancy, but really, all it's doing is drawing the best possible straight line through a bunch of data points. So if you want to predict a house price, you just find its size on the chart and see where it hits the line. Simple as that. Now, for choosing between categories, you got something called a decision tree. And honestly, the best way to think about it is like a game of 20 questions. The algorithm learns to ask a series of simple yes or no questions that slice and dice the data until it narrows it down to a single answer. Then you've got this one called k-nearest neighbors, or KNN. People call it a lazy learner because it doesn't really do any work up front. When a new piece of data comes in, it just looks around at its closest neighbors. The K in the name is just how many neighbors to look at, and it takes a vote. It's basically the you are the company you keep algorithm. And you know what? It works surprisingly well. Okay, now this is maybe one of the most important concepts in all of machine learning. The real goal isn't just to be right about the data you've already seen. The real test, the thing that separates a good model from a useless one, is how well it performs on brand new data it's never seen before. That's called generalization. So let's look at this. You've got two models trying to separate the red dots from the blue dots. On the left, a simple, straight line. It makes few mistakes. On the right, this crazy, complicated, squiggly line that gets every single dot perfectly right. So, which one is actually the better model? What does your gut say?
It might seem counterintuitive, but almost every time, the simpler line on the left is the one you want. Why? Because that complicated model on the right hasn't actually learned the pattern. It's just memorized the training data, noise and all. The second you show it a new dot, it's probably going to have no idea what to do.
This massive problem has a name. It's called overfitting. And the analogy of studying for a test is perfect. It's the difference between actually understanding the concepts and just memorizing the answers from the practice sheet. You might get 100% on the practice test, but you're gonna bomb the final exam. Okay, before we finish up, let's give you a quick little toolkit, a few keywords you're gonna hear all the time if you look more into this stuff. First up, a feature. That's just a fancy word for an input, like the size of a house. Then you have the model. That's the finished product, the program that actually makes the predictions. And finally, the training set. That's just the data you use to teach the model in the first place. It's the textbook it studies from. And there you have it. We started with what feels like magic, telling dogs from pastries, and ended up with a method. We've seen how machines can learn with an answer key, how they can find patterns on their own, and why it's so important for them not to just memorize the answers. The magic really is just a method, a very clever one. So that leaves just one last question for you. Now that you know the fundamentals, what real-world problem would you want to teach a machine to solve?